Okay, today we're going to talk about general launch angle kinematics and projectile motion. And we're going to start out just with an example of a ball being kicked. And we want to know how far the ball travels. So that's going to be our delta x. And we know that the ball is kicked at a velocity of 20 meters per second at an angle of 30 degrees. Okay, so I need to start out writing down my variables, and I've got Vx, V naught x, Ax, delta x, and t, and then I also have Vy, V naught y, Ay, and delta y. So I start out writing down all the things I know, and I know that this ball is going to land at the same level that it started out at, so I know that delta y, the vertical displacement, is 0. I know that in the y direction the acceleration is negative 9.8 meters per second squared, and I know that delta x is what I'm looking for. Since nothing is pushing this ball forward after it leaves the foot, it has an acceleration in the x direction of 0. And that means that my initial x velocity and my final x velocity are going to be the same all the way through. Now I need to find v naught x, and I need to know what v naught y is as well. So I look at my initial velocity right here, and that is the hypotenuse of a triangle. So I'm going to pull that out. We'll do that right here. So here's v naught equal to 20. And I know that there's an x component and a y component to that initial velocity. The angle again is 30 degrees. So v naught x is the adjacent side to that angle. 20 is the hypotenuse. And that means that I'm going to use cosine. The cosine of theta equals v naught x over v. My adjacent over my hypotenuse. If I multiply both sides by v naught, I get v naught x equals v naught times the cosine of theta, and that's going to be 20 meters per second times the cosine of my angle of 30. So I take my calculator and I go 20 times cosine of 30. I get 17.3. So my initial x velocity is 17.3 meters per second. That's also the same as my final x velocity. Now for v naught y, I do the same thing, except I'm going to use sine. So sine of theta equals v naught y over v naught. I multiply the v naught up to here, so I get v naught y equals v naught sine theta. And that's going to be 20 times the sine of 30. 20 times sine of 30 is 1/2, so 20 times 1/2 is 10 meters per second. So that's what I can put down right here, 10 meters per second. Now I also know that this initial y velocity, v naught y, is the same as the final y velocity over here, vy. It's just the opposite, so that's going to be negative 10 meters per second. That's only if the ball lands at the same level as the from where it was kicked. So to find delta x, I first look at my x variables and I determine whether or not I have enough information there to solve, and I don't. I only have v naught x, vx, ax, and delta x, and you might say, well, I could use equation 4, but that one won't work because the term that has a and x in it is going to become 0 since ax is 0. So I have to get time, but I'm going to get it from my y variables. So this becomes a question mark as well, and I know everything. And basically, I can use any equation that has time in it. And so I'm going to use the easiest one. That's equation Vy equals V naught y plus AT. AYT. All right, I'm going to move V naught y over to this side. So I have Vy minus V naught y equals AYT. And I'm going to divide both sides by AY and cancel out AY. Now I can plug the numbers in. Vy is negative 10 meters per second minus V naught y, which is just 10 meters per second, all over negative 9.8 meters per second squared. I do the math and I find that that comes out to be 2.04 seconds for time. So that's going to go up to here. So let's write 2.04 right there. All right, now in my x variables, I have everything I need. So I can go delta x equals V naught xt plus 1/2 axt squared. Ax is 0, so that whole term goes away. And now I just plug 17.3 meters per second times 2.04 seconds into the V naught xt, and that works out to be 35.3 meters per second. So that's the range. That's how far the ball will go. Now let's ask another question. How high does the ball go? What's the highest point? So what's delta y right here? So for this problem, I'm going to redo my variable table. So Vx, V naught x, Ax, delta x, t, Vy, V naught y, Ay, and delta y. Okay, delta y is what I'm looking for. How high does it go? Ay, again, is going to be negative 9.8 meters per second squared. V naught y will be the same as it was up here. That's the starting velocity. So that's going to be 10 meters per second. And Vy at the top of the path here is equal to 0. That's where it's turning around, going from going up to going down. So that's 0. Well, I already have enough variables now here to solve. I don't have to do anything with my x variables. So I can use equation number 4, which looks like v squared equals v naught squared plus 2a delta y. Vy squared is going to be 0. I'm going to move v naught y squared across, so I have negative v naught y squared equals 2a y delta y. And then I'm going to divide both sides by 2a y. So cancel that out, and now I've put my numbers in. Negative 10 meters per second squared divided by 2 times negative 9.8 meters per second squared. So that's going to be negative 100 meters squared per second squared divided by negative 19.6 meters per second squared. Get my calculator out again. So negative 100 divided by negative 19.6, and I get 5.1 meters for the maximum height. Now let me do one more variation of this problem. We'll start with the same information, 20 meters per second, 30 degrees. But this time I want to know, what is delta y when the ball has traveled 30 meters. So in this case, I have the same information I had from before. V naught y equals 10 meters per second, and V naught x equals 17.3. And go back to the beginning of the video if you're not sure where those numbers came from. So let's do our variable chart again. Vx, V naught x, Ax, delta x, and t. Vy, V naught y, Ay, and delta y. Alright, in this case we're looking for delta y. Ay again, negative 9.8 meters per second squared. V naught y didn't change. And in the x direction we know that x is 30. We know that A is 0 still, and V naught x is still 17.3 meters per second. So I again look at my y variables to see if I can solve for delta y if I can, just using those variables, but I can't because there are only two things here. So I come back to my x variables. I know I'm going to have to find the time. So I've got V naught x, Ax, delta x, and t, which means that's going to be the third equation of our 4. So that's delta x equals V naught x t plus 1/2 axt squared. Ax again is 0, so that goes away. I want to solve for t, so I'm going to divide both sides here by V naught x, and they cancel out. And so delta x over V naught x is going to be 30 meters divided by 17.3 meters per second, and that equals 1.73 seconds. So that's my time. So that's going to shoot right up to there. Now, in my y variables, I have time, V naught y, Ay, and delta y. Again, I'm going to use the same equation just with y's this time. And so that's delta y equals V naught y t plus 1/2 Ay t squared. Now nothing goes away, but I don't have to do any rearranging. I just have to plug the numbers in. So this is going to be 10 meters per second times 1.73 seconds plus 1/2 times negative 9.8 meters per second squared times 1.73 seconds squared. So I get my calculator out here. I go 10 times 1.73 plus 0.5 times negative 9.8 times 1.73 squared. And I get negative 12.93. That's not right. Let's try that again. 10 times 1.73 plus 0.5 times negative 9.8 times 1.73 squared equals 2.63 meters. And there you have it.